All right, next example, picking back up with this polar area stuff. Here we go. It's a sketch, set up the integral expression to find the area inside the graph of r equals 3 sine theta and outside the graph of r equals 2 minus sine of theta. It says do not evaluate. All right, well, let's graph these things. Let's do the limison first. Okay, so let's do this. Remember, r equals 2 would be a circle. That's going to look, oops, that's not really very close to 2. Fix it. There we go. R equals 2 is going to look more or less like that. And then it's pushed downwards, right? It's got negative y direction, so it's going to be pushed down 1. So that means the horizontal points don't move. That point gets indented 1. Notice if I set it out 2 and I push it down 1, it's going to only have a dimple. And then that point also gets pushed down. So here we go. That one's going to look kind of sort of like this. And then you're going to have that little dimple. That's kind of an over-exaggerated dimple. Whatever. And then we have the other one, which is a circle. It's a circle. It's on the y-axis, and it's going to go up to 3 units. So there we go, right? That's where it would go up to, I don't know, more or less like that. That was actually pretty bad. I don't know. That was probably equally as terrible. Oh, well. So let's look. Here's the region, right? We have this intersection point, and we have this intersection point. They're going to be symmetrical. And then we're going to be trying to find the area of this region in between the two. It says find the area inside the circle, but outside the little limison, right? So inside of the circle, but outside of the limison. Well, I'm going to have to find what those intersection points are, right? And then really, I'm going to have to do the area inside of this, right? If I find this area, or actually, if I find all of this area from this angle to this angle, right? I'm going to find all of this area first, and then we'll just subtract the area from the green limison. So really, this one, we're just going to have to find the big area and then subtract the little area. We've got to find those intersection points first. So let's go for it. I need to know what angle are these things going to cross. That's my theta 1. And then I need to know what angle are they going to cross and intersect again. So let's go set those things equal. Let's go find the intersection points. 3 sine theta is going to equal 2 minus sine of theta. Add that over. So we got 4 sine theta equals 2. Divide by 4. Sine of theta equals 1/2. The sine being 1/2, there's 2 angles on the unit circle. There's pi over 6. And then the other one over here would be the 5 pi over 6. So there we go. We got the intersection points. This one is going to be the pi over 6 angle. And then this one is the 5 pi over 6. So then we're pretty much ready. We're just going to take the big area and subtract the little area. Here we go. Let's write it. We're going to have 1/2. Don't forget about the 1/2. Pi over 6. 5 pi over 6. Now, we can't do outside minus inside and squared, right? Because the formula is 1/2 r squared d theta. I really have to do the big area minus the small area. I can factor out the 1/2 if you want, so that's good. I could combine it, right? So I could factor this out to the front. I could even combine the integrals since they intersect. But I cannot factor that out. So I can't do r minus r and then square it, right? I can't factor out that exponent. But I could end up doing the big R that squared and then minus the little r, kind of like washers almost. But 1/2, we can factor that out. Then I'm going to need the big R, which was the circle. So I'm going to have 3 sine theta squared. That's getting me all the area inside of the circle, right? That's getting me all of this. But then we don't want all of that. We want to take that and then subtract the green area right here. And then that's going to end up getting us just the yellow. We kind of declutter this. There we go. So then we're going to minus the other one, and that's going to be 1/2. Got that factored out. And then here we go, 2 minus sine of theta squared. And then that's it, right? There's our area of that region inside of the circle, but outside of the limison. It says do not evaluate. Good, I didn't want to anyways, question, but we don't have to. Right, so there we go, very good. Could we use symmetry? Yes. If we had wanted to, instead of doing from pi over 6 all the way to 5 pi over 6, I could just do from pi over 6 to pi over 2, right? And then if I were to find this, that's half, and then I could double it to get the other side. So I could have also done this, right? If I double it, that's going to cancel the pi over 2, and then here, or sorry, it's going to cancel the pi of the 1/2. So I could also do pi over 6, so this angle to pi over 2, that's only half, and then so if I double, right, the doubling is what cancels, right? Having the 2 and the 1/2, they cancel. So you could have it like this, pi over 6, pi over 2, and then have no coefficient out in front. That's really taking half of the region and then multiplying by 2 to double. Could we do that? Yes. Are we going to want to? I don't know. If we had to do it by hand, probably, but we don't have to do it by hand, so it doesn't matter, right? Could I use symmetry to maybe make it look different? Sure. But that's probably what you'd want on the AP exam. All right, very good. Let's do the next one then. The next one's going to be a little bit harder because it's got a sneaky little area. It says sketch and set up the integral expression. Again, we're going to find the common interior this time, though. That means it's going to be inside both. It's got 3 cosine theta. So that one is going to end up being a circle on the x-axis. It's going to go out to 3. That doesn't look very much like a circle. Oh well, kind of close. And then we'll have the r equals 1 plus cosine. That one's going to be a cardioid, and that one's going to be on the positive x-axis, right? If I think about the r equals 1, probably, yeah, I guess I can probably do red. If I think about r equals 1, that's what it would look like. Then you're going to push it to the right 1 unit. That means that point stays the same. That point stays the same. That one gets moved to the right. That one gets dimpled back. That one gets pushed exactly to the pole. So here we go. That one. And then there we go. Let me see if I can get rid of those extra dotted lines because they're kind of annoying. There we go. Come on. And then come on. Here we go. There we go. And we want the common interior. That means inside of both. So we have this, right? We have all of this region. Which, because of symmetry, we're actually going to focus. Could we do the whole thing? Yes, but we're going to use some symmetry. And we're going to focus on just this top part, right? I can see that I've got the intersection point, but we're just going to find the top part, and then we're going to multiply it by 2. But what's going to be a little bit difficult for us, and I don't know if I can do this small enough. I wonder what's that going to do? Oh, that's the one that draws a shape. Yeah, I guess I'll just have to probably do it small. What we're going to see is like if I actually draw that little intersection point. Right, so that theta equals, and I don't know what that intersection point is, but really, if I'm doing a common interior, I basically only need to know what's the smaller one, right? And so really, to get this region, all I'm going to have to do is integrate the red function, because the smaller, right, if it's common interior, if it's inside both, you really only need to know which one is the smaller one. So integrating the red is going to get us all of that region, right? Let's call that region 1. The problem is we have a second little sliver. We have this region 2, which is right there, right? It's kind of hard to see, but it would be like right there inside the green, but out. So yeah, I don't know. I just can't speak English, I guess, right now. But this one's kind of a little bit sneaky, right? We've got that region 2, which is really thin, which is really the green is the innermost curve. It's really kind of hard to see, but I don't know, there it is. You can kind of look on the graph, and that's a little bit more noticeable. But we're going to have to integrate the red to get that first region, and then just integrate the green to get that little sliver, the second region, and then we'll just add them together. But yeah, there we go. Let's go for it. We've got to find the intersection points first. So again, set those things equal to each other. 3 cosine theta equals 1 plus cosine theta. It's Friday afternoon. I can't hardly speak. Oh well. 2 cosine theta equals 1. This is the cosine, going to be equal to 1/2. Cosine being 1/2, that happens here and there. That's pi over 3, and then that one's 2 pi over 3. So these angles, this one is pi over 3, and then if we wanted to know that one, it would be either negative pi over 3, or you could also use, that's not 2/3 pi. Ooh, gosh, ooh, that was bad. That's not 2/3. That's definitely 5/3. 1, 2, 3, 4. That's definitely 5/3. Gosh. So it's not 2/3. It's 5/3. 2/3 would be in quadrant 2. I don't know what I'm thinking. You would probably just want to use the negative angle instead. But oh well, it doesn't matter. We're not even going to fuss with it. Could I do negative pi over 3 to pi over 3? Yes. But we're going to have to kind of break this up anyway, so we might as well just use symmetry. What I'm going to do is I'm going to integrate from 0 to pi over 3, and then when I do 0 to pi over 3, really all I need is the red function. And that's going to give me that region. And then from pi over 3, I'm going to have to figure out where is the green one going to be back at the pole. Right? So let's go take that green one and let's set it equal to 0. 3 cosine theta is equal to 0. Cosine is equal to 0. Let's see. Cosine is equal to 0 where it's at the top and at the bottom. So there we're going to go. Pi over 2. That's where the green function, that's when it gets back to the pole. So I'm going to need to do two intervals. I'm going to need to do 0 to pi over 3. And in that little angle, I'm going to be only integrating the red, only the circle. But then from pi over 3, which is the intersection point, to pi over 2, that's when I'm only going to be working with that green part to get that little sliver. And then once I've kind of done all that work to identify, then we can actually just plug it into the formula. And it's not too terribly impossible. Here we go. Area. I'm gonna only use symmetry, right? So we're only doing this top part, so I know I'm gonna have to double everything. So there we go. But that first part, I've got 1/2, and then from 0 to pi over 3, and then we had the red one. So it's 1/2 r squared. So we've got 1 plus cosine theta squared. Come on, smart board, what are you doing? Why are you doing this to me? D theta. So there's that first region 1. And then I need to add the next one, which is going to be 1/2, and then that's from pi over 3 to, it was pi over 2, and then we had the other one, which was the circle, 3 cosine theta. There we go. And if I took the region 1, which is kind of that bigger, more obvious region, which is inside the red, and then I take that little sliver, which is inside the green one, that's kind of between the pi over 3 and the pi over 2. If I take both of those and add them together, that's going to give me my total region. Of course, since we're going to divide, since we're only doing half of it, then I would take this and I would multiply it out, and that's actually going to end up canceling. So I could just have this 0 to pi over 3 of 1 plus cosine theta squared. That's the region 1, but doubled. So now I've got this region and that region, and then plus, then I have the pi over 3 to pi over 2, and then we had the 3 cosine theta. And then when I double it, that gets me the little sliver, and it gets me the other little sliver down there. And so either one of those would be fine. Like in symmetry, you can just do half of it and then double. But yeah, this is probably the one in the black. That's probably the best looking version. If you had to do it by hand, that's probably the one that you would want to use. Yeah, there it is. All right, so that one's a little bit nasty, but it's not the end of the world. 1/2 r squared. It's pretty easy formula actually. Yeah. All right, let's go for it. Let's clear this out. Okay, I don't want that. Go away. Let's go to the next page. We got 2 more pages. Hopefully I can get it all done in this one video because I'm kind of tired of making these videos. We're only at 13 minutes, so I think we're doing okay. Let's go ahead and look at this one. This is a pretty long free response question. You can tell it's a free response because it's got multiple parts and it's free response. This is an old AP exam question. Let us go for it. Here we go. It says a graphing calculator is going to be used on this example. That's good. Right? A curve is drawn in the xy plane and is described by the equation in polar coordinates, and it gives it to you. 2 plus sine 2 theta. And it's 4. It gives me the theta restriction, 0 to pi. Or r is measured in meters. Theta is measured in radians. Part A, sketch the graph of the curve. Don't mind if I do, calculator. Don't mind if I do. Let's just graph it. All right, so we're going to use our graphing data calculator, and then we're going to see the graph, right? See graph. It gives me that graph. Very good. Let's go graph it. Here we go. Let's get the calculator. Where is it? Where is it? Where is it? There it is. Let's get out of here. Let's do this one. It's 2 plus sine 2 theta. Bam. I'm going to actually turn the football off. It doesn't really matter. I'll just leave it actually because I don't care. That's good. Let's go look at this. The theta step that it told us, or it told us it was just between 0 and pi. So just between 0 and pi. And then the theta step, that's probably okay. Let's look at it. Ooh, all right, it's going slow. I could have probably turned my theta step up. Oh well. Ooh, all right, here it goes. It looks kind of like almost a river, and then oh, it bounces. Oh, it's so slow. There it goes. Kind of a weird looking shape, almost like half of a peanut or something. I don't know. I got kind of that bulge and that kind of right side, and you got that little kind of lame part over on the left. I don't really know how to describe it. The lame part. Oh well. Let's sketch it. It did start at 2. That was how. That's where it started at 0, and it does actually intercept up here at 2. But it's got kind of this bulge, and it actually intercepts over here at 2 also. But it kind of does something like this. It kind of has that little bulge. It kind of does something like this, and then it kind of has that like lame part over there. That's like more or less kind of what it looked like, right? It may not be perfectly to scale. Okay, like if this was an AP exam, they're not going to give you graphing on an AP exam, but we would make it a little bit more accurate. That's more or less what it looks like. All right, so that part's done. Awesome, thanks calculator. Now let's do the next one, which is, let's find the area. Here we go, the area, it's 1/2, and then it gave us the limits, right? It was 0 to pi. It told me the limits, and it's just r squared. So we've got 2 plus sine of 2 theta squared d theta. And that's going to be finding, right? That first little wedge at 0, then that one, that one, that one, right? We're finding all these little areas of all those little sectors from the angle 0 all the way to the angle pi, right? Instead of having these horizontal or vertical rectangles, we really now have these angles that pivot around through specific angles. And then again, we would just use our calculator to end up getting this. Let's go back for it. Okay, let's see. We got 0.5, math 9, and then we got 0 to pi. I always forget if this works. Let's see. If I hit vars, y vars, we're in polar mode. We have it typed into y1. I feel like that should work, but I also know I don't really fuss with polar mode in the calculator very often. Let's see. Ooh, that is the correct answer. That's the answer I have on my answer key. So that looks like it works pretty well. Just like how when we're in rectangular mode, function mode, we can use y1 and y2, vars, y vars, y1. If we're in polar mode, we can do that again. Keystrokes for it, you can look kind of at the bottom. It was vars, then you scroll to the right. But since we're in polar mode, you actually have to scroll down to polar, and then you can click either wherever you have that thing typed in. But yeah, don't forget the 1/2 out in front. That's the thing that students are probably going to miss out. 1/2 r squared, 7.68 if you truncate, or 7.069 if you round. So I'm gonna truncate 7.068. 7.068. We could probably put units on this if we wanted to, because it did give me some measurements. R is measured in meters, so that would be meters squared. I bet if you probably didn't put units, you would probably be okay. But since there's units in this question, right, we had meters and we had radians. Again, that's going to tell you, make sure you're in radian mode. It's really rare that we ever use degree mode, but that tells you specifically radians. All right, there we go. Part B's done. Now let's look at the interesting part, part C. It says, find the angle theta that corresponds to the point on the curve with the x coordinate of 1. -1. So I can see like x equals -1, like I can see that. And I know there's a point. It may not be exactly at that point where the little depression was, but there is a point on the curve where the x coordinate would be at -1. But remember for polar, right, we want x to be -1. For polar, we know x is r, I said r, and then I wrote x. X is r cosine theta. And so we're going to want r cosine theta to be -1. And we can plug in our r value. Right, so that's 2 plus sine of 2 theta. And we're going to need r times cosine. So there we go. And then we're going to end up using our calculators to get this. Now, we don't really want to have this in polar mode. We're going to actually want this to go back to function mode to end up finding the intersection point. But we know x is equal to -1. Could I type that in as a vertical line? Yeah, you would just have to kind of switch it, and you'd have r equals -1 -1 secant theta, right? So if we wanted to type it in, we could, but we're not gonna, right? We're just gonna switch it back to function mode, and then we're gonna use the calculator to find the intersection point. Kind of walk us through, right? Type the left side into y1, type the right side into y2, and then we'll be able to get that intersection point. So let's go for it. Let's go to our calculator. And let's switch it back, mode. Let's switch it back to function mode. And then let's type this stuff in. We had 2 plus sine 2x. There's r, and then we had cosine theta, so cosine x. There was the left side of my equation, and the right side was just -1. Let's just graph these. Let's graph it and find the intersection point. And remember, we were living between 0 and pi, so I'm actually going to come back to this window, and I'm just going to look at it between 0 and pi. That's all I need, 0 and pi. So I need that intersection point, right there. That didn't probably show you that right there. I'm clicking on it. I don't think you can see it. Second trace, let's calculate. We need the intersection point, so 5. First curve, yep. Second curve, yep. The guess doesn't really matter, but if you want to, scroll over closer toward your intersection point. And then there we go. X equals, remember, X here is representing theta. So we're getting the 2.63, yada, yada, yada. Okay, I'm going to store that just in case I need it. So I got X, stow, alpha A, just in case I need it, right? But I got 2.630. Remember, the calculator was using X. That's just because our variable button. But here we used the calculator, and we found the intersection point. We got theta equals 2.63, and then the units would be radians. Sure, just box it. All right, part C is done. That was kind of a little bit weird, but not too bad. Now part D says find dr d theta at the instant where theta equals 5 pi over 7. It says what is our angle? What does this answer tell us about r? We could do this, right? This function r. That's pretty easy, and we could take that derivative ourselves. But this is a calculator question, anyways. So I don't have to. Remember, math 8 is how you can do derivatives in the calculator. So we're going to do this, right? We're going to use our graphing data calculator. We're going to use math 8. But I'm just going to take the derivative of r, which is 2 plus sine of 2 theta. And we're just going to math 8 it, and then we're going to tell it to evaluate at the 5 pi over 7. Right, the math 8 in the calculator, that's how we can do the derivatives. I think you can do this either in polar mode, or I think you can do it in rectangular mode. Let's go check. Let's go check. Now, in polar mode, I don't need the whole thing typed in. Right? I don't need the intersection point anymore. So let's get rid of that. Let's get rid of that. So I've got r typed in. I don't need that. Get out of there. So that's the r function, 2 plus sine 2x. Now, I know I can do math 8. Math 8, I know is going to work in rectangular. It's just going to use x. And I have that r value. I have it typed into y1. And of course, it's 5 pi over 7. I know it's going to work in rectangular, negative 0.445. So this was negative 0.445. The units for r over the units for theta. Units for r were meters. The units for theta were radians. So that's like meters per radian. It's kind of a weird one. That's okay. It probably doesn't really care a whole lot about the units on this question. But I need the units for r, right? Taking the derivative of r. So it's the units for r over the units for theta. But there we go. Let's check and see if we can do it in polar mode also. Let's switch back to polar mode. I'm kind of just curious. I don't remember. I think you can. I think the intersection point's the only one that's weird in polar. Let's try. Math 8, ddr, or dd theta, and then let's see. I think I have it typed in. Yep, I still have that thing typed in. So I've got, I just need to go snag it. Bars, y bars, we're in polar mode. R1, d theta, so it's 5 pi over 7. I think it's going to work. Yeah, look at that. It still worked. It's really just the intersection point that you don't want to do in polar, because I can't really graph -1, because r equals -1 is not a vertical line. We probably could, but I think also if we look at this graph, oh, it's going to go slow. If we look at the graph, I regret this. If we look at the graph, ooh, that's kind of a weird scale. Oh well. It's because it's really wide, but the y-axis is, the y-scale is too big. If we were to try to graph the vertical line, it's just easier to do it in function mode. But anyways, let's go back to this. We got that dr d theta. We got it 2 different ways. So that's good. But now it says, what does this tell you about r? What does this tell you about the curve? Well, dr d theta was negative. Therefore, right, since dr d theta is less than 0, r is decreasing. Right? We know that if the derivative is negative, then that thing is decreasing. Right? That's what this part says. R is decreasing. What does that tell us about the curve? Therefore, the curve is, remember, the distance r. I don't know, 5 pi over 7. That's pretty close to 1. So that's actually probably more like over here. R is the distance from the pole to a point. Right? Here the r was 2. Here the r was, I don't know, something. Here the r was this. Right? That function describes the distance from the pole. That's what polar things do. Right? They describe not x's and y's, but it says, hey, based on this angle, how far away from the pole are we? So we know r is decreasing. So what that means is that our graph is actually going to be getting closer and closer and closer to the pole. Since r is decreasing, that means the distance to the pole is decreasing. So the curve is approaching or getting closer to the pole. R is the distance to the pole, right? That's conceptually what it means to be graphing in polar. Based on the given angle, how far away are you from the pole? Since r is decreasing, the curve is getting closer to the pole, aka the origin. Then we got this last part, E. It says a particle is traveling along the polar curve. Here's why it gave us the meters, right, for the kinematics in part E. It says a particle is traveling along this polar curve given by this function r, so that its position at time t, which is parametrics. Ooh, here we go. It's combining the polar and the parametrics. Here we go. Its position at time t with an x function and a y function such that d theta dt equals 3. And it says find the value of dx dt at the instant when theta equals pi over 6. This says interpret the meaning of my answer in the context of this problem. This is like, okay, what does that mean? Let's read it again. Particle's moving. Okay, so we got kinematics. It's moving along that curve. So we have some particle. Let's see, what color haven't I used? All right, we have some particle, and this thing's moving, right? It may start here, and then it's like moving along this. Instead of moving just horizontally along the x-axis or vertically along the y-axis, it's just moving along this curve, right, according to parametric functions. Right, so that's what that particle will look like, right? It kind of does something more or less like this. And we're trying to figure out dx dt. That's the horizontal velocity. We know kind of the overall position. We know r, and then we know d theta dt equals 3. We're probably going to have to use that. And it says find the value of dx dt. And it gives us the theta value that we're looking at. Okay, well, let's try to just start with the basics. If I want dx dt, I somehow have to get x and then take the derivative with respect to t. So let's go for it. Let's do part E up here. I know x is r cosine theta, right? Okay, so that means let's plug it in. X is going to be, plug in the r value. It was 2 plus sine 2 theta, 2 plus sine 2 theta, and then times cosine. That's what x is equal to. Now, the problem is that that doesn't have t's. And so that's a problem. I can't take the derivative of t if there's no t's. So let's try to think about units. If I want dx dt, how can I potentially get it to work? Well, I have x, but it's with respect to theta. So I could take dx d theta. That's not a problem. That's no problem, but I need to do something because dx d theta is not dx dt. I would have to multiply by d theta dt. You guys catch that, right? I have x in terms of theta, so I can do this, right? And I could do that either myself with product rule, or I can use the calculator. I can get dx d theta, but somehow I would have to, in order to get everything to line up correctly, I would have to take dx d theta and then multiply it by d theta dt. That way the d thetas cancel, giving me dx over dt. I kind of have to think about this one a little bit harder. This is weirder. I can do dx d theta, but then I would have to multiply it by d theta dt. But luckily, what did it tell us? D theta dt was 3. So here we go. I know this is just going to end up being 3. So that's really nice. So now I just need to get dx d theta. I know what x is. I could take that derivative using product rule, or we can just use the calculator. and then we can take that number and then we're going to multiply it by 3. All right, so let's go back. Let's get dx d theta. Dx d theta would be the derivative of this thing, the derivative of 2 plus sine 2 theta cosine theta, right? That's x. I'm going to take the derivative of it. Of course, we're going to use our graphing data calculator. And so let's go get this dx d theta. Again, using the calculator, we're going to do a math 8. Here we go. Let's get out of there. Get out of there. I don't care. Clear. You can do this either in parametrics or in the function mode. It doesn't really make a huge difference. Let's just go for it. Math 8. We have d theta, and then I need r times cosine theta. So 2 plus sine 2 theta, close the parenthesis for the argument, close the parenthesis for r, and then I need cosine of theta, close that parenthesis. So I'm going to have this take the derivative. Remember, that's x. X is r cosine theta, and then it said plug it in at theta was pi over 6 was the angle. Pi over 6. And so that's going to give me dx d theta. X is r cosine theta. Plug in the r value, and then that's all going to be, right? X in terms of theta. I can do dx d theta. It's negative 5.66. Come on. Come on. You can do it. Come on. Come on, smartboard. You can do it. I believe in you, kind of. This is going to be negative 0.566. That's dx d theta, right? That's not what we wanted. I would then have to take this, plug it in right here, and then multiply it by 3. And then I'm going to end up getting dx dt. All right, so let's go back to the calculator. All we got to do is times 3, bam, negative 1.709. So I've got negative 1.709. All right, let's see. I don't really have a whole lot of empty space. I can probably get rid of that stuff. All right, this is all the work for E. Oops. This is all the work for E. Okay, so let's summarize it. We got dx dt is negative 1.709. Let's think about the units. The units for x, horizontal distance, that's going to be in meters. And then time, does it give us a time unit? I don't think so. Yeah, so we don't even really need to worry about it. Notice, like nowhere in here does it give me a time unit. So I don't need to worry about the units. There's my dx, there's my dx dt. Kind of a little bit of troublesome to find, but let's answer this last part, right? We found the value of dx dt. Now we have to interpret the meaning of it in the context of our problem. Well, here, dx dt, it was less than 0. Therefore, that particle is moving. What do we think? dx dt, that's going to tell us horizontal. That doesn't tell us up or down at all. Right? We don't know. But dx dt tells us if it's moving to the right or if it's moving to the left. And since dx dt was negative, I know it's moving to the left. And that's all we know, right? Moving to the left, since it's negative, that's really all we got. But that's the application. That's really the interpretation in the context. Since dx dt was negative, I know at that point it's moving to the left. I don't know really where it is on that curve, but it's moving to the left. If dx dt was positive, it would have been moving to the right. But yeah, there we go. Long question, but now we're done. We got one more, and this last example is going to be similar to that one we just did. So let's do it, and then we'll be done, not just for today, but for the year. I'm excited. Here we go. I'm coughing all over the place. Here we go. Let's see, where's my scroll button? There it is. Last one. All right, here we go. A curve is drawn in the xy plane, and it's described by this equation in polar coordinates, and it gives me, again, that polar of theta plus cosine 3 theta. Here it gives me the restriction pi over 2 to 3 pi over 2. So that's going to be at quadrants 2 and 3. That's from 90 degrees to 270. So that's going to only be on the left side of my graph. For r is measured in meters, theta is measured in radians. Part A, find the area. This is much the same as the last one, except it doesn't have us graph it, which is nice. We're going to probably want to graph it anyways. Let's go for it. Part A. I'm going to just sketch the graph. Let's go to the calculator and let's look at this thing. Let's see. Clear. Let's get out of here. Let's clear that. And let's do, what is this? Theta plus cosine 3 theta. Cosine 3 theta. Bam. I'm going to change the window really quick. I don't really know. I'm just gonna do. It's probably not super big because the coefficients are over here. I'm just whatever. Let's just do -10 to 10 just to be careful. Oh, that's the theta. Oops. The theta I knew was from pi over 2 to 3 pi over 2. It gave me that. It gave me that in the question. Pi over 2 to 3 pi over 2. Theta step. Okay, I don't really need it to graph super slow. Let's make it 5 times faster. Okay, here we go. The x-min. Let's just do. We know we need the left side. So let's try -10 to. We don't really need to go very far. Let's do -10 to 5. Let's see what that looks like. Oh, I didn't need that much on the y, right? Okay, so there we go. Let's kind of trim this down. I don't need so much vertical, and I don't need to go so far to the left. So I don't need so far to the left. How about let's just try -5, and I don't need the y values to go so big. Let's try -5 to 5. Let's see what that looks like. Oh, I kind of kept it on there. I'm just gonna change it just because I'm weird. I'm gonna change that to -6 just so I can get that. Ooh, not the scale. No, not the scale. Get out of there. 1. Let's put this to it's the minimum. That's -6. Just because I like to see everything kind of safely. But this is going to be a pretty good. Yeah, it's kind of like a peanutty shape. Again, only from pi over 2 to the 3 pi over 2. So only on that left side. Let's sketch it. Of course, anytime you use the calculator to do something, you should sketch it. All right, so here's what that graph kind of more or less looks like. There's my x and y axis. Here we go. It started off something like this, and then it looks, ooh, no. It did something like this. It went up a little bit, and it was like this, and then kind of almost like a butterfly or something. But there we go. That's kind of more or less what our graph of r is going to look like. All right, and that's r equals theta plus cosine 3 theta. So we got it with the calculator. Very good. Find the area bounded by it. Here we go. We're going to find this area. It told me the angle restrictions, right? It was pi over 2, and then we're going to rotate all the way to this bottom one to 3 pi over 2. All right, so the part A is pretty easy. Area equals, don't forget the 1/2. Don't forget that it's r squared. This one was pi over 2 to 3 pi over 2, and then plug in the r values, theta plus cosine 3 theta. There we go. And again, we're just going to use our graphing data calculator, and we're just going to math 9 it. All right, let's quit out of there. 0.5, math 9. Here we go. It was pi over 2 to 3 pi over 2, and then I need to do r squared. So bars, y bars, I'm in polar mode. Have it in r1, r squared. And there we go. Let's see. I just need to define the variable. Bam, 19.674 or 675. Again, you can either round it or you can truncate. Doesn't matter. I'm just going to say 674. 19.674. So area equals 19.674. I'm not hugely worried about these units because the last question, I knew it, we didn't really end up caring. But there we go. There's our area. Not super bad. There we go. Part B. Find the angle that corresponds to the point where the y-coordinate is 1. That's similar to what we did on the last question. But here on part B, I want y to be equal to -1. Y is r sine theta. So I want that to be -1. Let's plug it in. Theta plus cosine 3 theta, right? That was my r value. Sine theta, that's going to be equal to -1. And we're going to switch this back to regular function mode. We're going to type that into y1. We're going to type this into y2. We're going to use the graphing data calculator. We're going to find the intersection point. And again, we're going to only want the intersection point between pi over 2 and 3 pi over 2. All right, so there we go. Y equals -1. We know y is r sine theta. Plug in the r value. We're going to have to graph the left side of y1, graph the right side of y2. Here we go. Y equals -1. Right, we can kind of visualize it. And there is a point on the graph with that point. But yeah, let's go find it. Switch it back mode. Let's switch it back to function mode. Let's go type these things in. Y equals, let's clear that out of there. And so we're going to have what's theta plus cosine 3 theta. Oops, I didn't get the 3, did I? Well, let's see. No, what is it doing? It's not registering my fingers. X plus cosine 3x. There we go. That's the function, and then we need to multiply that by, we were doing y, so it's by the sine of theta, right? So it's r sine theta. There's the r value. Then I need sine of theta. There we go. And then we need this to be -1. Let's go. There's multiple intersection points, but we're going to need the one between pi over 2 and 3 pi over 2. So we're going to want the one on the right. Okay, so let's go trace it. Second, trace, calculate. Let's go get the intersection point. First curve, yep, we are on the first curve. Second curve, yep. The guess, I don't know, 3. I don't know, that's probably pretty close to it. There we go, 3.4849, whatever, about 3.484. Okay, I'm going to go store that just in case I need it. I'm going to take x, store it in alpha a, just in case. Last time we didn't need it, but 3.485 if you round it, or 3.484 if you truncate. So here we had theta equals 3.484. The units for that would be in radians, right? We know that. The units for the area would have been in meters squared. You could have put it, but honestly, I don't really think it matters that much. But now part B is done. Let's look at the part C. It says, for what values of theta is dr d theta positive? What does that say about r, or what does it say about the curve? Okay, so we're going to have to do a sign chart. Dr d theta, we have r. We can take the derivative, or we can just graph the derivative, right? That's probably faster. So for part C, I know, again, r was theta plus cosine 3 theta. So that means dr d theta, we can do this. The derivative of theta would be 1, and then the derivative of cosine 3 theta is going to be minus 3 sine 3 theta. Let's just graph. I can't spell. Let's just graph with the calculator, and then we're just going to find where, if we want this graph, we want it to be positive. We want it to be above the x-axis. So there we go. We're going to use our calculator. We're probably just going to do it in the function mode also. We're going to find that derivative, type it in, and we're just going to be looking at where it's positive. All right, so here we go. Let's go back to the calculator. We're in function mode. I think, yep, it tells me, yeah, I guess it doesn't say. But I'm pretty sure I'm in the function mode. Let's switch it. Yep, we are in function mode. Get out of there. And then let's go ahead and type in that derivative. I'm going to, just in case I need those anymore, I'm going to just turn those off just in case I need them. Sometimes I'm careful. Actually, I can just clear it out because I can put -1 back. But here we go. Let's do the derivative. It was the derivative of x was 1. The derivative of cosine 3x is going to be minus 3 sine of 3x. There we go. Remember, we only care about this interval, so I'm going to go change this window. I only need it to be from pi over 2 to 3 pi over 2. I'm going to change the scale. I'm going to change it pi over 6. That's probably fine. Let's see. Y min, Y max. Yeah, that's probably fine. Ooh, no, I don't want to do that. Pi over 6. There we go. Let's graph it. So there is my derivative. There's my dr d theta. That's the derivative of r. And it looks like, actually, let's go back. I realized something when I looked at my notes key. It doesn't even want the whole thing. The whole graph, right, it told us was from pi over 2 to 3 pi over 2. What does it want here? It only wants it between pi and 3 pi over 2. So we're only going to do pi to 3 pi over 2. So let's go fix it. I did pi over 2. I was doing more. I did more. So let's go look at the window. I don't want pi over 2. I just need pi. I said pi, not clear. Let's do, I didn't need a second. Let's do pi. And then again, that one was your 3 pi over 2. There we go. There we go. So a smaller piece of the graph. It looks like it's positive for the most of it, negative underneath it. So we could go ahead, right? We're going to need to find that intersection point. So second, calculate the 0, the left bound. Yep, that looks on the left. The right bound. I think 4 is going to be somewhere close to the right, pretty safe on the right. Ooh, actually, that doesn't look very good. Let's get out of there then. Let's go do that again. Second, calculate the intersection, or the 0, the x-intercept. Left bound, okay, here we go. I guess we'll just have to scroll. Oh, that's why. Yeah, there we go. see how far over was that? It's at 4.5 or something. So you need to type in like a 4.4. Oh well, you can just scroll somewhere on the left, somewhere on the right, and then there we go. Guess, and it looks like it's 4.302. I'm gonna go save that. So I'm gonna take X, store it in alpha B just in case, but it's 4.302. And then that graph, it was positive before, it was negative underneath. So if we were to go to this, we could do our little sign chart. Really, we only care about this interval from 0, or sorry, not from 0, from pi to 3 pi over 2. It started off positive, and then until that value, which was 4.302, which I have stored in alpha B, it was above until it got to that point. That's where it was equal to 0, then it was negative, and then it was negative up underneath it as well. And so what does that mean? Right, the derivative was, so I guess answer the question. Right, it says find the value of theta on the intervals, find the values. I'm definitely on still part C. I circled that wrong thing. I'm really glad that it's Friday and I get to go home in about 20 minutes as soon as I'm done with this video. But anyways, here we go. Now, pi to 3 pi over 2, that is the correct one. Where is it positive? So let's go for it. Dr d theta is positive 4, and then it gives us the interval, and it was 4 pi to that intersection point, 4.302. Bracket on the pi because it was above, and then parenthesis on that one because it was 0. There we go. There is where the derivative was positive, so that part's done. What does that say about r? If dr d theta is positive, then r is increasing. Duh. So that answers this. What does it say about the curve? Remember r is the distance, right? R is this distance from the point on my curve to the pole. So if r is increasing, that means the curve is going to be moving away from the pole. Right? Since r was increasing, that means the curve, can't spell, still, the curve is moving away from the pole. That's kind of the opposite of what we saw in the last one. If the dr d theta was negative, that means r was decreasing. That means, hey, like it would be doing something like this, where it's coming back towards the pole. But here, since the r is increasing, it's got to be on a stretch like this, where that distance, right, to the pole is increasing. It's moving more away from the pole. Yeah, there we go. All that's done. Finally, we did the derivative, we graphed it, we just looked to figure out where it was positive. We did the interpretation. That meant r was increasing, which means the distance to the pole was increasing, which means the graph was moving away from the pole. Ooh, all right, 2 more parts, and then we're done. I'm so ready to be done. Oh, well, 2 more parts, and then we're done. Part D, it says find the value of theta, also on this interval between pi and 3 pi over 2, that corresponds to the point on the curve with the greatest distance from the origin. Oof. And it says, what is that greatest distance? Okay, so really what we want to do, right, is we want to maximize r. R is the distance to the pole, right? So here it says the greatest distance to the origin. Really, that's r, right? And I want to find the absolute maximum over this. So that just means do candidates test, right? We're going to do candidates test, and we're going to find what's the absolute maximum of r on this interval. And then, yeah, there we go, candidates test. What's nice is we've already done a lot of the work. We've already done a lot of the work because we've already looked at the derivative. Here it changed from positive to negative, right? So it's increasing to decreasing. So that was a relative max, but I've already found the critical points. I already know my endpoint, I already know that endpoint, and I already have found the critical point. So really all that's left is I just got to bring all this together and do my little candidates test table. I don't really have a whole bunch of room. I'm going to delete the green stuff because I think we're done with the part B. I think we're done with this. Hopefully it doesn't delete everything. Sometimes it does. There we go. All right, here we go. Let's do the part D. So we're doing candidates tests. So I need the R values. Actually, not the R values. I need the theta values and then the R values. We know the endpoints. Got to test pi. Got to test the 3 pi over 2, and then the critical point that we had, that was that 4.302. I'm glad I stored it, right? I always, anytime I do anything with the calculator, I always just store it. That way, in case I need it later. I honestly don't remember doing this question from 2 years ago. I'm glad I stored it. That way I don't have to waste the time. Let's go take all these things, and all we got to do is plug them into the R function. Okay, and then we're going to figure out which one's the biggest, and then we'll be good to go. So let's go look at this. I need the R. I don't have the R. That was the derivative. So I'm going to turn off the derivative. And then here, that's R sine theta. I don't need that. So let's delete that. Let's delete that. Let's delete that. Okay, there we go. Now X, now that's just, now the Y1 is R, right? X plus cosine 3X is theta plus cosine 3 theta. Very good. Let's go now evaluate this. Let's do vars, Y vars, Y1. And let's plug in pi. And then it looks like 2.141. 2.141. Here we go. 2.141. The distance for this would be meters, I think. And then we need to plug in the alpha b value, which I have stored, and 3 pi over 2. So let's go get those really quickly also. So let's go take this same thing, but now I need to plug in, let's go plug in alpha b, which is 5.244. 5.244. And then we need to do the 3 pi over 2. So let's go back to the calculator. Let's go snag that again. And then let's go forth and do 3 pi over 2. 4.712. 4.712. Here we go. 4.712. All right, we're ready. That's the maximum. So let's just write out the sentence. The maximum distance. Let's see. How did it phrase it? The greatest distance to the origin. The maximum distance from the origin. Did it say origin or did it say pole? Origin pole to the curve. I said to the. I wrote it backwards. Oh my gosh! I'm really glad today's Friday. To the curve, from the pole to the curve, is 5.244 meters when theta equals 4.302 radians. There we go. Right, remember, the table by itself isn't the answer. Don't just do this and then say done, right? No, the table is the supporting work, but it wants you to write it out, right? The absolute max is blah when x equals blah, or the absolute min is blank when x equals or t equals. Like here, the maximum distance is 5.244 when theta equals 4. Oh my gosh, 4.302. I'm dying. Justify my answer. We don't need to justify it, right? The justification is the table. That's the supporting work. Right. Remember, R is the maximum, the distance from the port. So you could also say like the absolute maximum of R, and then R basically is, right? R is the distance from the origin to the curve. So you could just say the absolute max of R is, probably should have said absolute in there also. But yeah, there we go. R is the distance from the pole to that curve. So there we go. We're maximizing it to Kennedy's test for R. We already had the critical point. There we go. Table's the justification. We got the greatest distance. It didn't even ask for the angle, but we gave it both, right? It just asked for the distance. Okay, last part, and then we're done. A particle is moving along the polar curve. Again, similar to what we did on the last one, so that its position is given by parametrics, x function and y function. It says d theta dt is 2. Find the value of dy dt at the instant theta equals 7 pi over 6. Let's get rid of this. Nope, that's not what I wanted to do. That's not at all what I wanted to do. Let's get rid of this. Let's see if this is going to work. Really? Why are you doing this to me? I'm so tired of this school year. It's almost over though. That's right. That's very good news. All right, here we go. Let's see what color. Let's do this one in. I guess let's do it in like dark green. All right, part E. Remember, y is r sine theta. So y is going to end up being theta plus cosine 3 theta times sine of theta. So there's my y. Now it's defined by theta. So like if I math 8 this, if I use my calculator to do math 8, it's going to tell me dy d theta. All right, so let's go for it. Let's take this derivative, and we're going to plug in theta equals 7/6. It's slightly bigger than 1, so that's going to be something like probably here, right? That's where our point's going to be. And we're going to see, okay, how's this thing moving? So let's go get this dy d theta. Let's go for it. All right, clear, clear, clear. Let's see, what do I have typed in? I have r. Nope, not that one. I don't need the derivative anymore. We got r, and then I need r sine theta, I think. Yeah, it was r sine theta. So there we go. Sine theta. Bam. So now I got that typed in, and then I will just have to math 8 that thing to end up getting what we want. All right, so we got r sine theta typed in, math 8 x, and then I got that thing typed in, 2 y1, and then it's at 7/6. 7 pi over 6. There we go. Here's our derivatives, negative 5.174. Negative 5.174. But remember, that's dy d theta. That's not what it wants. It wants dy dt. It wants the kinematics. It wants the rate of change of y with respect to t. It wants that y velocity. What I have is dy d theta, right? The angle, the horizontal or the vertical position changing based on the angle. All right, so let's go back and think about it again. Remember, dy dt, what would I have to do? Well, I would have to take dy d theta, and I would have to multiply by d theta dt, because unit-wise, that's how I would get everything to line up, and I would get dy dt. I just did dy d theta. That was the negative 5.174. This thing is really testing my patience today. The dy d theta, we just did that. We got it with the calculator doing math 8. And then the theta dt, it told us here again, it told us that was 2. So I have to go now is take that thing, multiply it by 2, and then we're going to have the answer. So here we go. That answer, it's going to be negative 10.348. There is your dy. Actually, I'm just going to label it. Whatever. That's my dy dt. Now, we got the dy dt. The last thing it says interpret the meaning, right? Since dy dt is negative, that means y is decreasing. That means the particle is moving downwards, right? Dy dt is going to tell us either if it's moving up or if it's moving down. Dx dt tells us left or right. Remember, last time we got a negative dx dt, so it was moving left. But the dy dt will tell us the vertical, either up or down. Here, since the d theta dt was negative, that means the particle is moving downwards, which we can kind of tell right here, right? It looks like the dx dt probably would have also been slightly negative, because it looks like that curve is still kind of bending outwards. Then it starts to curve back, and on that section, the dx dt would be positive. But here it's still going down, going down. Maybe over here it's coming back up. Right? If you think about each one of these points as like a little vector, you have the horizontal component, which is the dx dt, the vertical component, which is the dy dt. But at that little moment, it was going downwards, right? So it's tracing this curve, it was going down. We don't know if it was going left or right. I would guess it was still going slightly left, but again, that's just a guess. There we go, we're done. Right? Those are kind of long questions, especially when they bring on that part E, where they mix the polar stuff with the parametrics and the vector stuff, which will happen occasionally. But there we go, right? Long questions, long notes today. The area bounded by, let's kind of recap, right? What's the important stuff from this video and the one before it? How do I find the area bounded by a polar graph? It's 1/2, and we integrate. We always have to find the limits for our integral, but it's just 1/2 r squared d theta, right? That's all you need for your polar area. Most of the time, the struggle is this. You're going to be given the r. That's easy. You just have to figure out what are the limits for my integral. Like, what are the intersection points between the two things? Or if I have something like this where it's going to do like one of those things, you have to figure out when does it get to the pole. So where's the r0? And sometimes if you only want one pedal, right, you could do the whole thing, divide it by 6 or divide it by 3, depending on how many pedals your graph, your integral traces. The formula is just 1/2 r squared d theta. That's not super difficult. Most of it, again, if it's non-calculator, you're just going to have to set up the integral. They're not going to make you do it by hand. If they do actually want you to tell them what the area is, they will give you a calculator. They won't make you do the area without a calculator. If it's non-calc, you'll just have to set it up. If it is a calculator, you may have to math 9 it. Either you can math 9 it in the polar mode or in the rectangular, the function mode, either way. 1/2 integration of r squared. That's how we do the polar areas.